Hey guys, welcome back to chapter 8. What we're going to talk about today is going to be the third type of reaction that you guys are responsible for. So in chapter 7, I told you there's going to be 4 reactions that you're going to know by the end of this unit. We learned the combustion and the alkali metal halogen reaction. Today, we're going to talk about precipitation reactions. There's a lot going on with precipitation reactions. So what we're going to have to do first is get some tools to put in our tool belt. We're going to have to get some skills learned first. Then we can dive into a precipitation reaction problem. So that's what we're going to do now is we're going to build up our skill set, and then we're going to dive into an actual problem. So precipitation reactions. Solubility. Solubility is the ability of a compound to dissolve in solution. The solutions that we typically talk about in General Chemistry 1 are water solutions, aqueous solutions. So if we say something is soluble, then it's going to dissolve in water. For these precipitation reactions, we are going to focus on just ionic compounds. So if they are soluble in water, what do we know about ionic compounds dissolving in water? We know that they dissociate, right? They break apart into their ions. So if it's soluble in water and it's ionic, what we will see is they will break apart into their ions and they will dissolve in solution. They'll become an aqueous solution, so just a bunch of ions floating around. There are some ionic compounds that are insoluble. So we take the ionic compound, we throw it into water, and it doesn't dissolve. Nothing happens. So what would we observe in that particular scenario? Well, we observe that solid that we threw into the solution would just float to the bottom and sit on the bottom as a solid, right? So here we see silver chloride is insoluble. It does not dissolve. So we would just see it gathering on the bottom of the beaker. And then we see this letter here that it's still a solid. Okay. So soluble dissolves in water, dissociates, breaks apart. Insoluble does not dissolve in water and would just kind of float to the bottom as a solid. Okay. So for precipitation reactions, eventually what we're going to get to is we're going to mix 2 aqueous solutions. So this beaker up here at the top has some sort of ionic compound dissolved in it. This beaker right here also has some sort of ionic compound dissolved in it. So 2 solutions with ionic compounds dissolved. When we mix those 2 solutions, we're going to predict if there's going to be some sort of solid that precipitates out. That's how we get these names. So we're going to see if there's a solid that precipitates out or forms, and we'll be able to predict what is that solid that forms, and we'll be able to use our solubility rules to determine what that solid is. So this is an example of a precipitation reaction. We mix 2 aqueous solutions, some sort of solid forms. So this yellow here is the solid that forms. And notice that solid settled on the bottom of the beaker. And there's also still some ions that are dissolved in solution as well. So we'll be able to predict what happens and where all of these ions are in solution. But that's a lot going on. So we've got to get some skills down first. We got to get some tools in our tool belt before we can work on this problem. So the first skill that we need to determine, or we need to have, is how do we determine if something is soluble or not? So if I have an ionic compound and I put it into water, I need to be able to predict, will it dissolve or will it not dissolve? So what I'm about to show you is a table from your textbook. In a face-to-face class, this table would be provided on the exam. So I suggest that when you start working on these problems, quizzes, exam, that you have this table in front of you. I don't expect you to memorize this. So this is the top half of the table. And the top half of the table focuses on compounds that are generally soluble. Okay. So an ionic compound that contains lithium or sodium or potassium or ammonium, any of the ionic compounds that contain these ions would be soluble without exception. So examples would be if I would throw something like sodium chloride into solution, that will always dissolve. If I throw potassium hydroxide in solution, that will always dissolve. If I throw in lithium bromide, that will always dissolve. So if the ionic compound has any of these ions present, it will always dissolve without exception, no exceptions. Okay. Ionic compounds that have these ions, so nitrate and acetate. So any compounds that have these ions also will dissolve without exception. So for acetate, it could be something like, let me make my life easy, rubidium acetate. Okay, so rubidium acetate, I don't even know if that exists, but if it does exist, this will always dissolve in solution because that acetate ion is present. So always going to be soluble. Chlorine, bromine, and iodine. So chlorine, bromine, and iodine are generally soluble. So most of the time they will dissolve in solution, unless they are attached to one of these guys. So silver chloride or mercury chloride or lead chloride will not dissolve. They will be insoluble. Okay, so these are the exceptions to the rule. If chlorine's attached to anything else, it will be soluble. And same goes for sulfate here. So generally soluble unless it's attached to one of these guys right here. Okay. So that's the top half of the table. Bottom half of the table are generally insoluble. So generally, if I have something with a hydroxide or a sulfide, an ionic compound that has a hydroxide or a sulfide in it, generally that will be insoluble. So most of the time it'll just remain a solid. It won't dissolve unless it's attached to one of these. So lithium hydroxide, soluble. Barium hydroxide, soluble. Anything else hydroxide, insoluble. Okay, so again, these are the exceptions that make it soluble. Other than that, it does not dissolve. And same thing with carbonate and phosphate here. So generally insoluble unless it's attached to one of these guys. Okay. So when we do these precipitation reactions, you're going to be able to predict what the ions are on the product side. Then you're going to need to be able to use this chart to determine, is it dissolving in solution or is it forming some sort of solid? So let's practice that skill, predicting if it's soluble or insoluble. All right, so why don't you go ahead and pause the video and look at these two and tell me if it's soluble or insoluble. All right, so the first one, sodium carbonate. So I see sodium is one of the ions. Let me go to my table. Oh, sodium's right here. Sodium, generally soluble. Absolutely no exceptions to the rule. So anytime I see sodium, I'm going to say, yeah, that's soluble. Okay. Lead sulfate. Okay, well, let me look here. I don't see lead. Oh, there's sulfate, right? So let me start there. Sulfate, generally soluble. unless it's attached to, oh, there's lead. So lead is the exception that makes it insoluble. Okay, so lead sulfate would be insoluble. Okay, so that's how we would predict that. Yeah, but am I going to give you the formulas on an exam, a quiz? No. What am I likely going to give you? Words. What I want you guys to do now, this stuff is not going away. It's going to come back over and over again. So what I want you guys to do is I want you to write the correct ionic formula for these two compounds. Then I want you to determine, is it soluble or insoluble? So pause the video and give it a try. All right, so cobalt hydroxide, cobalt 2 hydroxide. So the first thing I want to do is I want to write the formula for cobalt hydroxide. So cobalt formula is CO. Hydroxide is one of our polyatomics, so it's OH. Okay. Now I need to think about the charges. So cobalt is a transition metal. It gave me this Roman numeral, so yay, I don't have to think. So cobalt is a 2+. Hydroxide is one of our polyatomic ions, so go look at your polyatomic ion list, and we'll see that hydroxide has a -1 charge. So when I go to write the ionic formula, remember I flippity-floppity the charges. So this is going to be cobalt hydroxide with a subscript 2. So that's the chemical formula for cobalt 2 hydroxide. So cobalt 2 hydroxide, is it soluble or insoluble? So let's look, see if we can find cobalt or hydroxide. No. Oh, there's hydroxide right there. Hydroxide is typically insoluble unless it's attached to lithium, sodium, potassium, ammonium, calcium, strontium, beryllium. Okay, so it's not attached to any of the exceptions, so that's going to make this guy, cobalt 2 hydroxide, insoluble. Okay. Barium nitrate. So chemical symbol for barium is Ba. Chemical symbol for nitrate. Nitrate is one of our polyatomics, NO3. Barium is in group 2A. So it's got 2 valence electrons. It's going to give those 2 away. It's going to have a 2+. Nitrate is a polyatomic. Go ahead and look that up, and we'll see that nitrate has a 1-. So to write the correct chemical formula, flippity-floppity the charges, we're going to have BaNO3 with a subscript of 2. So there's the chemical formula for barium nitrate. Is barium nitrate soluble or insoluble? Okay, so let's see if we can find barium or nitrate. No barium. Whoop, there's nitrate right there, and there are 0 exceptions to the rule. So nitrate will always be soluble, so this is soluble. Okay. So the skills that we have practiced are writing ionic formulas, so that hopefully that's a review. And the other skill that we practiced is predicting whether it's soluble or insoluble by using this table. Okay. So let's move forward into a precipitation reaction. So here's what it's going to look like. I would say something like lead nitrate reacts with potassium iodide. Write the balanced chemical equation. So you would have to identify this as a precipitation reaction. So a precipitation reaction is when a solid forms upon mixing two aqueous solutions. So lead nitrate, aqueous, potassium iodide, aqueous. So we got to predict what are the products, and then we've got to decide which one of those products is the solid that forms. Okay, so predict the products, determine the solid. So for precipitation reactions, they're sometimes called double replacement. So what happens in precipitation reactions is these two ionic compounds just flippity-flop partners, right? So lead is a positively charged ion. Nitrate, negatively charged ion. Potassium is a positively charged ion. Iodine is a negatively charged ion. So when these guys flippity-flop partners, there's really only one option that makes sense. If lead comes over here to look for a new partner, is he going to be attracted to potassium? No. Positively charged lead, positively charged potassium, those two are going to be repelled by each other, right? So think two north ends of a magnet pushing against each other. So the only new partner that makes sense for lead would be that negatively charged iodine, okay? So that would be our first product, would be lead and iodine would come together. And then the other guy here is nitrate. So if nitrate wants to find a new partner, he would come over here. Would it make sense for nitrate and iodine to come together? No, they're both negatively charged. Again, they'd be repelled by one another. So the only partner that makes sense for nitrate would be this positively charged potassium. So the other product is going to be potassium nitrate. Okay. So that's the first thing we need to consider is the flippity-floppity of the ion partners, right? Well, now that we've gotten the new ions onto the paper, well, now we need to make sure that they're neutral, electrically neutral, right? We can't just give them a new partner and leave them with a charge. That would be no good. Okay. So let's go back and think about this. This 2 right here tells me that the charge on lead must have been a 2 plus. Nitrate is always a 1 minus. Potassium is in group 1A. He's always a 1 plus. Iodine is in 17 or 7A. He's always a 1 minus. Okay. So when we picked up our new partner, we had a 2 plus that got together with a 1 minus. So what do we need? That's not electrically neutral. What do we need? Yeah, we need a 2 down there, right? And then potassium was a 1 plus, nitrate was a 1 minus, 1 and 1, those balanced, so no subscripts needed there. Okay. All right, so flippity-flopped some partners. Whoopsies. So let me just rewrite this down here. Lead, nitrate, plus potassium iodide. They're going to flip-flop partners and give us lead iodide, potassium nitrate. What's the last thing I need to do here? Is this a balanced chemical equation? Nope, it's not a balanced chemical equation. Okay. So take inventory just quickly here. We've got lead, and there's only 1 of them. Nitrate, there's 2 of them. Potassium, there's 1. Iodine, there's 1. Come over here. Lead, there's 1. Nitrate, there's 1. Potassium, 1. Iodine, 2. Okay. All right, so we could start anywhere we want. I see that there's 2 nitrates here, only 1 over here. So I'm going to put a coefficient of 2 in front of our potassium nitrate. That changes that to 2. Also changes that. And then I come over here and I say, oh, iodine and potassium need changed. Well, good thing they're attached to each other. So I put a coefficient of 2 there, and now we are balanced. So there's our balanced chemical equation. Okay? Lots of steps in these precipitation reactions, I know. So we mix these two aqueous solutions. We predict what their products are. We balance that chemical equation. The last thing we need to do is decide which one of these is the solid that formed. Okay? So to find out which is the solid that formed, we're going to look solely at the products, right? So we knew the reactants were aqueous. So we're going to focus our attention over here on the products. Okay? So let's start here. Potassium nitrate. So we would go to our chart. We would come up here, find potassium or nitrate. Oh, there's potassium. Always soluble. There's nitrate, always soluble. Yeah, so pretty good indication that this is going to be soluble. Okay, so you could either write soluble, or the way that you'll write it probably in your homework is an S after it. Oh, nope, not S for soluble. The way you'll write it in your homework is an AQ, that it's aqueous, that it's dissolved in solution. Okay? So let's look at lead iodide over here. Whoops, go back to our table. All right, so let's find lead or iodide. Nope. Nope. Oh, there's iodide. And it's generally soluble unless it's paired with one of these, and there's lead. So when lead and iodine come together, the result is insoluble. So this is insoluble. It would form a solid in solution. It would not dissolve. So that would be our solid. That would be the S, our solid. Okay. So the next two slides are going to walk you through this same problem. So here is where we have the reactants. Then I broke those reactants apart. So I broke them, let me get my pointer here. I broke them apart into their ions, so I could very easily see who's going to flip-flop partners, who would make sense. And then I put our products down, and I also made sure that our products were electrically neutral. So when I write an ionic compound, one of my jobs as a chemist is just to make sure it's electrically neutral. And then I predicted which one would be the solid in solution and which one would be aqueous. And this is also where I see the balance too. So what would this look like? What did we just do? It's kind of hard to wrap your brain around this when we're just looking at letters and numbers, okay? So here's what we have. Here we've got our aqueous potassium iodide. So in this beaker right here, it's an aqueous solution. The potassium iodide is dissolved in water. So these red and white things kind of in the background is the water, and the silver and purple are the potassium iodide dissolved, okay? Originally, so if you kind of look right here in the beaker, originally in the beaker was aqueous lead nitrate. So again, these red are the nitrate, yellow are the lead, dissolved. As soon as our potassium iodide hits the lead nitrate, that's when they flippity-flop partners, and we see this yellow solid form in our solution, right? So this yellow solid is that insoluble compound. It's that lead iodide that's crashing out of solution. So what we see here is our product, the end of our reaction. We see the potassium and nitrate are still ions floating around in solution because they're aqueous. And we see our lead iodide coming together as a solid, and it's going to eventually just kind of settle to the bottom of that flask. Okay. So that's an example of a precipitation reaction. So let's put this all together. Okay, big problem coming up here. Ooh, lots of words. So something I could absolutely do to you, something that's perfectly acceptable. A precipitation or precipitate. So precipitate is just a fancy word for a solid forms. A precipitate forms when aqueous solution of ammonium sulfate and barium chloride are mixed. Write a balanced precipitation reaction equation and identify what the precipitate or what the solid is. Go. Pause the video. Go. Okay, so let's work through this one together. There's a lot of steps here. So that word precipitate is going to be your indication that this is a precipitation reaction. That's going to be kind of the word that I use to clue you in, like, hey, you need to start thinking about this type of reaction. So a precipitate forms when ammonium sulfate and barium chloride are mixed. So let's start getting those on the paper. So ammonium sulfate, both of those are polyatomic ions. So if you have lost that polyatomic ion sheet or chart, I'll post one in helpful handouts. It's probably a good idea to have that accessible. So ammonium sulfate, ammonium is NH4. It's got a positive 1 charge. Sulfate is SO4. It's got a negative 2 charge. Okay. So when ammonium sulfate come together, they flippity flop their charges. We would see that the neutral formula would be NH4, the subscript 2, SO4. Okay. That's going to react with, or it's going to be mixed with, barium chloride. Barium chloride. Okay. So barium is Ba, chloride or chlorine is Cl. Barium is one of our main group elements, so it's always going to have a positive 2 charge. Chlorine is one of our main group elements. It's always going to have a negative 1 charge. So when barium chloride comes together to form a neutral compound, they're going to flippity flop their charges, and it'll be BaCl2. All right, so we mix these two compounds together. We're going to get 2 compounds out on the other side. So think double replacement or switch partners. So ammonium, who is his new partner? Who's the only one that makes sense? Yeah, chlorine. So ammonium and chlorine are going to come together. Okay. Ammonium is a positive 1, chlorine's a minus 1, so they can just come together as NH4Cl. Okay, so they balance each other out. And sulfate also needs a new partner. Who's the only one that's left or the only one that makes sense? Barium. So barium and sulfate are going to come together. Sulfate's a minus 2, barium's a plus 2. So again, 1 and 1, they come together and balance each other out. Okay. So we've gotten our reactants onto the paper. We've gotten our products onto the paper. We've made sure that those ionic compounds are neutral. Now we need to balance this equation. Why do we need to balance it? Because it told us to, right? The balanced precipitation equation. So we're going to have to balance this now. So take inventory. If you didn't catch this in the last problem that I did, if you have polyatomics that stay together on both sides of the equation, so here I see ammonium and ammonium. If you have a polyatomic that stays together on both sides of the equation, you can go ahead and just keep those together and treat it as one thing. You don't have to break it apart into nitrogens and hydrogens. That's even more to keep track of. So you can keep it together as ammonium as long as it stays together on the other side. So just a little helpful hint. So now I have 4 things to keep track of instead of 6. All right, so ammonium on the reactant side, I've got 2 of them, 1 sulfate, 1 barium, 2 chlorides. On the product side, I have 1 of everything. Okay. So ammonium is not balanced, but if I put a coefficient of 2 right here, that's going to change ammonium to 2. That's going to change chlorine to 2. And boom, that balances our equation. Okay. So we must have 2 of those molecules that form when this takes place. All right, friends, we are almost done. So we have our precipitation reaction. We predicted the reactants. We predicted the products. We balanced the equation. The last thing that we're going to do is determine what is the solid that forms and what stays as an aqueous ion. Okay, so ammonium chloride. Let's click back to our table. Oh, there's one right here. Cool. Ammonium chloride. So let's look for ammonium or chlorine. Oh, there's ammonium. Never an exception. So anytime you see ammonium, it will always be soluble. So this would be our aqueous. This would still be dissolved in solution. And then we've got barium sulfate. Okay, so let's look through here. Sulfate, there you are. Oh, well, sulfate's generally soluble unless it's attached to, oh, there he is. There's barium. So when he's attached to barium, that results in an insoluble compound. So this is insoluble. So when barium sulfate forms, it's going to be a solid that settles out, precipitates out. Okay. So again, this is a heavy problem. Again, this very easily could be worth 6 to 8 points on an exam. Putting the ionic formulas down, balancing the equation, identifying the solid. This is a heavy duty problem. So make sure you do practice some of these. I want to talk about one more scenario before I wrap up this video. So let's think about this following scenario. What happens if I were to mix together potassium iodide and sodium chloride? So go ahead and see if you can predict what the products are, and then what is the solubility of those products. All right, so flippity flop our partners. So potassium's positive, iodine's negative, sodium's positive, chlorine's negative. Okay, so flippity flop, we would have potassium chloride, and we would have sodium iodide. And the good news is everybody here is a +1 or a -1. So this all shakes out pretty easily. It's balanced, it's electrically neutral, blah, blah, blah. Okay. All right. So let's see the solubility of these. So let's look at potassium chloride. So potassium. soluble all the time. Okay, so this would be aqueous. And then sodium iodide due to sodium, soluble all the time. So this would also be aqueous. Okay, so let's picture what this product side would look like in a beaker. So I mixed potassium iodide and sodium chloride. I mixed these two, right? And then I let it settle out. And what would it look like? Well, potassium and chlorine would be ions floating around, right? Aqueous, soluble. And sodium and iodine would be ions floating around. So looking at this beaker, is anybody really interacting with anybody? No. They're all kind of floating around on their own. So if we mix two aqueous compounds and we get two aqueous compounds on the other side, we say that there is no reaction, right? So we mixed two solutions where the ions weren't interacting with each other. And when we mix those two solutions, the ions still aren't interacting with each other, so nothing is going to happen. We're going to see no changes in that solution. So when both products are soluble, no reaction takes place. And here's a visual of this, right? So here's our potassium iodide. It's aqueous. So gray and purple are just floating around, not interacting with each other. Here's sodium chloride. It's aqueous. So sodium and chlorines floating around, not reacting with each other. And then we put all of these ions together into a beaker, and they are still ions not interacting with each other. So here's sodium and iodine and potassium and chlorine, and none of them are touching each other. So we would say no reaction. They're just kind of hanging out in the beaker, but not reacting with each other. Okay? So if both, go back here. If both products are soluble, we would say there's no reaction. That would be your answer, no reaction. So that's it for precipitation reactions. Again, that's the third reaction that you'll be responsible for predicting the products, balancing the equation. So I hope you guys found that helpful.